So it's my pleasure to introduce Makoto Kelp. He's a NOAA climate and global change postdoc at Stanford, working with NOAA Diffenbaugh. And he really works on problems sort of the intersection of climate, wildfires, and policy. Makoto's actually from Seattle, so he grew up around Bellevue area, and did his undergrad at Reed College, where he got his bachelor's in 2019. And he actually worked at UW for 2 years with Julian Marshall, and also collaborated with Nathan Koontz, developing emulators to accelerate chemical mechanisms. Following that, he did his PhD at Harvard, where he finished in 2023. And during his time there, he received awards both in teaching and outstanding presentations at AGU. And finally, he was also recently recognized by the atmospheric chemistry community as an emerging senior scientist at the Gordon Research Conference for his work on machine learning on these interdisciplinary problems. And one final note, I don't know if CS knows, but our department has a band, and Makoto actually plays jazz trombone. So important point there. Anyways, on that note, I'll let Makoto take it away.
All right, thanks so much for the nice introduction, and I'm thankful for this opportunity, and I'm fired up to be here. So I start by saying that we are living in an unsustainable world with increasingly ill-equipped strategies and tools. Here, sustainability doesn't just refer to a general sense of environmentalism, but how we fundamentally construct and confront the problems that we face. And you know, it takes little to motivate this room of the importance of how destructive out-of-control wildfires can be on ecosystems, on infrastructure, and that of human health from wildfire smoke. However, we really have very little mitigation capability to tackle wildfires in the western United States. You know, we don't have the technology to put out large wildfires. They're simply too hot to just dump water on. We don't have the infrastructure or really the desire to increase the use of prescribed burning to restore landscapes resembling that of an indigenous America. And to be quite honest, even if we did, we don't know if it will work in preventing future fires. We then use to monitor these wildfires and different disturbances in the atmosphere using unequal observational systems. They're unequal in time, such as a satellite passing by once every several days to measure an atmospheric column. They're unequal in space, such as the location of air quality monitors in an urban airshed. We're going to have blind spots. And they're also unequal in equity, with a lot of these resources situated to monitor predominantly higher income and wider areas than the national average. We then use these unequal observations and feed them into these global climate and atmospheric models that are becoming increasingly unattainable in the ways we can run them. These models require hundreds of supercomputer cores to run, to the point where large centers and weather forecasting agencies are the ones running these models, even though the scientific advancements are done by research groups. So in many ways, these models are becoming more undemocratic in the ways we can access them. And my research looks at these different kinds of problems using data-driven and machine learning methods. And today we'll go around the world here, where we'll start with how we can use machine learning to alleviate the most computationally expensive bottleneck in these global atmospheric models. We'll then use elements of computational sensing, compressed sensing, to look at different variability trends in air quality at different scales across the United States, and how we can look at recent prescribed fires in the western US and what that looks like in preventing potentially future wildfires. And throughout my research themes, I try to incorporate elements of environmental justice and policy throughout. But first, let's start with this research theme, one of machine learning for atmospheric models. How I would rephrase this section is bringing modern machine learning into current atmospheric models. And so I start this section by saying that right now, our scientific advancements are outpacing our ability to model it. Here on the x-axis is time over the last 40 years or so. The blue dots and the right y-axis correspond to our current computing capability. And you see these are the number of flops or operations that our supercomputers can do. It roughly follows a trend called Moore's Law, which states that every couple years we get a roughly doubling of computational power. This is largely a hardware-driven phenomena where we're putting more transistors onto microchips. The orange circles and diamonds here represent our climate models that we use. And these are the climate models used in the IPCC assessment reports that dictate global climate policy. But you're noticing that the model resolutions of these climate models are starting to veer away from this Moore's law line. That even though every year we're getting more and more computer power, that the resolutions of these models are not keeping up. This is because we're not only trying to get high-resolution atmospheric models, we're also increasing potentially complexity. We're adding more parameterizations, more physics-driven numerical schemes to these models that are really starting to compete with our ability to get high-resolution models, to the point where right now, that even though we're gaining more compute power, these models are getting slower and slower to run. And so if I were to open up each of these global atmospheric models and look at the components that dominate this cost, what we find is that atmospheric chemistry, when it's included, is a bottleneck. In fact, global modeling of atmospheric chemistry is considered a grand computational challenge. And so this figure on the x-axis is the number of computer cores or resources we devote to a simulation. And on the y, it's the time that it takes for each of these components to run. And you notice that chemistry dominates the cost of a simulation. This is because chemistry, often described as a chemical mechanism, is very high-dimensional, typically involving hundreds of evolving species in time and space, which is in contrast to a lot of weather and climate variables, which may be lower in that dimensionality. But really the kicker here is that this chemical mechanism is incredibly numerically stiff, meaning that the atmospheric lifetimes found can vary by orders of magnitude. It's incredibly multi-scale, for radical oxidants that could last less than a second in the atmosphere to greenhouse gases that last for decades. And they're all described by coupled systems of differential equations in which you need a very resource-intensive solver to get the solutions to. And really, the bottom line right now is that adding any kind of detailed chemistry into an Earth system model or into a climate model is infeasible. These models already take weeks to run on supercomputing resources. If you included atmospheric chemistry, they would take months. But I argue that atmospheric chemistry is actually crucially needed to understand processes of air pollution on long-term timescales, aerosol radiative feedback effects into the climate system, greenhouse gas chemistry, and how all of these interact with climate. And in many ways, the climate models we have right now have very kind of coarse chemistry in them, if at all. And so I identified that machine learning methods may be a solution to this problem. That neural networks, for three specific reasons. One is that they're considered non-parametric universal function approximators, depending on who you may ask, meaning that they can map any input to any output regardless of the complexities or the non-linearities of these relationships, of which I show you a pretty cartoon example here of ozone chemistry, where ozone is a pollutant that behaves very non-linearly with respect to these other chemical species. Two, these neural networks can learn to predict based on large data sets of repeated patterns. If you've ever run a global atmospheric or climate model before, you know that we can generate a lot of data really easily. And three, and potentially most important, is that neural networks are shown to speed up solutions to these differential equations by orders of magnitude. Because what we're essentially doing is replacing that expensive numerical high-order solver with a series of input-output mappings that, at the end of the day, can be basically considered matrix multiplication once it's trained. And so I'm showing you here that past machine learning chemical solver attempts have been very unstable due to this rapid error accumulation. So this is work I started before graduate school, actually here at the University of Washington with Julian, who's in the audience, where I created a chemical machine learning solver for a zero-dimensional box model. So this box model is kind of an idealized framework of chemistry that happens in just one point in space. What I did is I generated a lot of data using this box model, sampling the inputs and outputs over a single chemical time step, and got really great training error results of my neural network. I then ran this model forward in time, such that the output is the input into the next time step. And by the end of 24 hours, it exploded with error. Sorry, Julian. But around the same time, another paper came out using a random forest machine learning integrator, a completely different machine learning algorithm, a completely different chemical mechanism, but still found this rapid error growth. However, I should note that this random forest was found to be 85% slower than that numerical integrator that you wanted to speed up, whereas the neural network here was much, much faster. So I wanted to go with this neural net approach of trying to correct this error instability. And so that's what I show here. This is one of my first projects in graduate school, was to correct this error. And I did so by building in physical knowledge of the atmospheric chemistry system into the machine learning architecture itself. So again, here I use a box model, and it has 101 species, both gases and aerosols coupled together, along with 4 weather forcing terms, being temperature, pressure, relative humidity, and the angle of the sun. And so the first thing I did was use an autoencoder. And so what this does is it takes my 101 chemical species and compresses it down into 16 features without loss of accuracy. You see, this is actually one of the tenets of data science itself, that any kind of high-dimensional physical system you have, that dimensionality is actually artificially high, that there's always some kind of lower dimensional embedding or subspace that we can project our problem onto. And in many ways, chemistry is no different, and we basically already do this with chemistry by grouping the species by chemical family or by similar reaction rates. What I then did is, instead of predicting the input-outputs over a single chemical time step, I had this neural network learn a time history, a diurnal evolution of chemistry, or a trajectory, if you want to call it that. What this does, it incorporates slower evolving chemical modes or reactions into this neural network architecture. So we know, or I should say that in my 2018 project that I showed you in that previous slide, that really what drives error in a system over a single chemical time step are very fast reacting species, usually radical oxidants. But we know that over time, fast reactions can actually be influenced by slow moving reactions or slow modes of a chemical system. A kind of classic example in atmospheric science is methane and the hydroxyl radical, where methane is this decadal, long-lived greenhouse gas. OH, or hydroxyl radical, lasts less than a second in the atmosphere. Over very short time periods, OH matters, but over long trajectories, methane can actually influence OH concentrations. And so using this machine learning architecture, where it's kind of physics informed, I get stable error within my 24-hour time horizon of interest, and really beyond that as well. And here I'm showing you the speed up we obtained using a neural network. So the top bar here is the time it takes this original Fortran-based numerical solver to integrate 1 million chemistry grid cells. It takes around 5 hours to do so, whereas the neural network on a single CPU level of resources can integrate the same 1 million grid cells in around a minute. So we have this orders of magnitude speed up in the ability to perform these calculations, and that can also be extended if you give it additional compute resources. But you know, I really want to discuss why we should and should not use machine learning in the context of atmospheric chemistry and these global models. Why we should? The chemical calculation is incredibly expensive. It's the complete bottleneck in these simulations, to the point where we don't include them in many climate models. It's highly repetitive. If you ever look at the output of an air quality model, you can see that there's so many redundancies in the system. Whether it's over the ocean or higher up in the atmosphere, one grid cell to the next is incredibly redundant. There's so many overlapping of these low dimensions. And so there's no need to actually call a full numerical solver to get those solutions. And also, it's fully deterministic, meaning that there's no element of stochasticity or randomness involved, because it's based on chemical kinetics, which are deterministic in this context. Why we should not use machine learning, however, is that the system is very high dimensional. A lot of examples of machine learning in the environmental sciences maybe have 10 or so input species or covariates to predict 1 or 2 outputs. Here we have hundreds of evolving species, inputs and outputs. 2, you know, these supervised machine learning methods, I would argue that they actually don't really learn physics. You have to build in those physical constraints into the model, and just banking on them actually learning anything is really contrived in many ways. And there's this idea that I've shown you these examples in very simplistic box model kind of scenarios where the chemistry is idealized. There's no guarantee that it'll scale to a global model. And finally, it's very difficult to implement. These global atmospheric models are largely written in Fortran, developed in the 80s, 90s, and really before then. These machine learning libraries are in Python largely. There's no native way to call Python from Fortran code. All right, so it seems like there's a lot of problems I have to deal with here. So in order to make my life a little bit easier, I used a lower dimensional chemical mechanism and tried to investigate what this looks like within a complete global 3D model environment. And so what I did is I used the super fast chemical mechanism, and it's very low dimensional, only 12 species. And it's supposed to be generally representative of ozone in the troposphere, of which I make comparisons in a zonal mean format here, compared to the standard chemical mechanism in Geoschem, which has over 200 species to describe the same kind of dynamics. Geoschem here being the three-dimensional atmosphere model that we will be looking at today. And so over a 1-hour chemical time step, I track 20 variables in the Geoschem model, being 2 physical variables, temperature and the density of the column, 6 photolysis frequencies that govern the change in sunlight govern the change in concentrations based on sunlight, and the concentrations of these 12 gas phase species themselves. And as you can see that even a 1-month data set over the 3-dimensional grid, I would have 62 million samples. So I have a lot of data to work with. I train all my models in 2016 and then test it in 2017, the following year. And so this is what this machine learning Python-based solver looks like when it's embedded in a more complicated global model ecosystem. What I basically did was I ripped out the guts of the Geoschem chemistry module and replaced it with this Python machine learning solver. And this took actually a huge amount of code-based alteration work because I had to design a tunneling system written in the C language so that these two modeling kind of frameworks can speak to each other and pass data between. But what I learned is that right now what I have is a fully embedded machine learning software library inside a 3D global model. And that kind of opens up a whole new possibility of how to train and deploy these models. Because what we know is that most machine learning studies that you'd see in kind of the literature deal with offline-based learning, where you generate a large data set, you curate and manicure that data set for the kind of scientific question you want to answer, and then you train your model on that data. Here, what we can do is online training, or we can actually train and interact the machine learning model inside Geoschem as Geoschem generates that data. So it's directly interacting with the physical model itself. And so that actually shows that these different ways of training these models produce different results on accuracy and stability. What I show you here is ozone metrics at the surface for absolute and fractional error, along with a time series of root mean squared error. All my models are trained in June, July, August of 2016, and then deployed inside Geoschem July of 2017. So this is this offline model where I just sample the inputs and outputs of a chemical time step. I get good training results, put in this model, and it immediately does crappy. So this is kind of what we see a lot. This is the most naive way to train these models. It's actually a very common result. It basically predicts an average kind of the 3D grid every single time step, because you have to be very aware of these training data when you kind of configure it. Next is I did this idea of training against a diurnal cycle, or trying to learn a trajectory of information. And you see that error is dampened quite a bit, down to around 20 ppb. But for the computer scientists in the room, that even 10 ppb of ozone error is kind of our upper bound of what is acceptable. So 22 ppb is still really bad for ozone error. But then what I did was I took this model, this diurnal model, which isn't great, but it's better than this T to T plus 1 model. I stuck it back inside Geoschem and retrained it online in Geoschem. And you see that dampened error down to 6 ppb. What I really hypothesize that is happening is that when you train a model online in a physical model that's generating that data, it's only the data that it can train on is only available at that time step. So it's actually ingesting and learning from a realistic representation of the 3D grid. And chemistry is really multi-scale, and there's so many different regimes that it's really easy to over or undersample different chemical environments when you just kind of generate this big data set and randomly mix it up into independent samples. But then I thought, why should I retrain a model where I have to train it offline, put it back in, retrain it online? That's a lot of work. What happens if I just train a model online from scratch to begin with? And that does the best by far. No real large spatial biases, and the error is the lowest out of all these different training routines. What I hypothesize that is happening over a retrained model is that actually when you train a neural net, it's actually difficult for some things to be unlearned from those networks. A lot of those weights are really well set in that network. And so you're basically starting with a biased prior, which we don't have to here. OK, and so as a result, I went forward with this completely online training approach from scratch. And this, I love showing this plot because it looks like just a bunch of squiggly lines and very uninteresting. But what I show you here is that for the first time, we have stable, year-long simulations of atmospheric chemistry in a global model with a fully machine-learned replacement. And so on the x-axis here, it's time over this 2017-year period. And on the y, it's the normalized mean bias relative to the reference solver in GeoSChem. OK? So there are a couple things I want to note. One is you notice that error does not explode or run away throughout this simulation. Two, that if you look at the inset of each figure, this is the year-long average error, and it's within 10% for all these species of interest, which is a target goal we had. But you do notice that there are different seasonal fits of accuracy here. What I did is I trained different sets of neural networks for each season. And so there's this kind of implicit bias that it's learned for a season. So any discontinuities you see in this time series, it's because I switched between these different sets of neural nets. And that's something to improve upon, obviously, for the future. What I want to note is I have this 5-time speedup in the machine learning solver over that of the reference solver. And you might say, well, that's not the 200-time speedup that you were seeing before. But this is because this is a very low-dimensional mechanism to begin with, so the speedup gains were kind of minimal. But what I really do want to draw your attention to is that other chemical transport model methods can only really get you up to 50% speedup. And that includes completely removing species and decreasing the accuracy of the solver itself.
If I can just ask a quick clarification
Yes.
question. So you're talking about training online versus offline. And I think the terminology that reinforcement learning people might use is sort of imitation learning these days versus, I guess it would still be online. Does that line up with what you're thinking, or maybe I can clarify a different way?
Sequential learning, as you can also call it that. It's basically only training on the data itself at each time step.
Simulation, which isn't actually recurrent on
Yeah,
the
exactly.
predictions or maybe.
Yeah, so it's a bit different. Yeah.
Yeah.
Okay.
And then that's all done in one run, and then you're applying it in a different run. where
Exactly.
It's not. Okay.
Yeah.
Cool.
All right, we'll talk more too. No problem, no problem. So I want to show here that the machine learning solver itself is actually very skillful. It can capture the dynamics of a polluted Beijing grid cell, where ozone chemistry is very dependent on human-driven emissions, but also that of Cape Verde, this very pristine marine atmospheric environment in which the variability of ozone is driven more by synoptic scale meteorology. You can see that it works in both areas still very well. And so the key takeaway for this section is that for the first time, we have these stable, year-long simulations of atmospheric chemistry in a global model with a fully machine-learned replacement. So it's the first time that's been happened at this, or done on this scale. Hasn't been done quite yet since, but I believe that there's a lot of interesting things to happen in this kind of field in the future here. So some ideas for current work is to be able to improve the generalizability of these models, right? I don't want to have a neural network for every different season or a neural network for every single grid cell. We want to be able to generalize to different conditions. What I also want to say is that what I learned throughout my research career is that there are machine learning communities for weather and kind of climate applications, but there really wasn't anything for atmospheric chemistry. So what I did was I started this, or helped co-found this initiative called Statistical Learning in Atmospheric Chemistry. It's an online Zoom group where we invite speakers, usually postdocs and grad students, the ones kind of on the ground developing these algorithms, and invite them to give talks and share their research to try to foster this community. We have over 50 members now across the United States and the UK, and this is something that's been a nice research highlight that I'm proud of. And so anyone can join too. So What I want to say is that I really believe that this is a huge opportunity in a very emergent area. The fact that now we have these fully embedded machine learning libraries that we can call inside the context of these existing global models really opens up a whole new world of opportunity. For example, the Julia language has these natively differentiable numerical solvers that gives you the adjoint of any solution or any calculation for free. To rephrase, you can get the sensitivity to any calculation automatically. If you were to do that in these kind of global established 3D models, it would require huge alterations to the code base to achieve that. OK, and now for something completely different. OK, so we're looking at computational or compressed sensing now. And this figure here on your right is a map that I've been very obsessed with for the past several years. This is the EPA, or the Environmental Protection Agency's Air Quality Monitoring Network. And this is a hugely important air quality network for our field. It's used to design and regulate air pollution control strategies and policies. It's used for industries it's used as a watchdog for industries that may be polluting above standards. It's also used to inform and validate these air quality models, which I just spoke to you about. And it's also increasingly used to attribute ambient health effects from air pollution. But you notice that it's very unequally distributed. You have way more sensors in the east than in the west. There's a prioritization of urban areas over that of rural ones. And there's also a higher density along the coasts rather than more inland. And so let me give you a little bit more context. PM2.5 is this pollutant that this monitoring network measures. It's an aerosol whose diameter is less than 2.5 microns. It represents the largest global burden of disease of air pollution in the world. So if you ever read anything linking air pollution to deaths, it's most certainly PM2.5. But what's really interesting to me is that PM has this very unique spatial temporal variability to it. It can come from a variety of different sources, whether it's from the tailpipes of cars or power plants, wildfires. It can even be chemically formed in the atmosphere itself. It's also very sensitive to weather conditions. It can be immediately rained out or travel slowly across the country if there's a favorable breeze. There's also this temporal element of PM2.5 as well, that over the past 20 years, and really since the 1990s, average air pollution concentrations are going down in the United States. Air pollution is getting cleaner. We're putting scrubbers in power plants and catalytic converters in cars, and this has represented a large policy win. To the point where even last week, we lowered the annual PM2.5 standard down to 9 micrograms from 12. So there's this level of inertia for air quality monitoring in the United States. However, as we clean up the polluting sources in the United States, that offers the opportunity for other sources to become the dominant drivers, with a lot of that being wildfires in the West. And you see that we have much fewer sensors in the West, so it's very difficult to kind of understand these changing dynamics both in space and time. And so you might think then, okay, why doesn't the EPA just add more dots to that map, right? The problem is that each of those dots costs $250,000 without the cost of upkeep or inflation. And so what's been really championed is that low-cost sensors or citizen science monitoring can fill in the gaps left by the EPA. Purple Air, being the largest low-cost sensor company in the world today, has been really championed as this democratic tool of air quality data. And so anyone can buy a Purple Air sensor, put it on the outside of their house, and connect it to the internet to upload these concentrations in real time. The problem is that this really great paper by Priyanka D'Souza finds that these Purple Air sensors are deployed in significantly higher income and wider areas than the national average. So there's this kind of built-in socioeconomic bias to it. But it's also deployed in areas with actually cleaner average air pollution than those with the EPA monitor. So we're not actually learning more information of the most extreme polluted places in the US. And so I wanted to ask the question, can we design a new optimal data-driven sensor network for the United States? Here, optimal meaning that we capture the pollution drivers of today. I should also note that a lot of those monitoring locations in the EPA network that I showed was deployed in the 1990s. And so in order to design a data-driven sensor network, I need good underlying data. Luckily, these machine-learned data fusion datasets have been just exploding in the literature today. How it works is you take a random forest or a regression tree-based model and dump a bunch of different covariates into it. That could be traffic data, satellite data, outputs from air quality models, and you can create these very dense, high-resolution data sets. I have this at over a 17-year worth period at a daily 1 kilometer scale. And it's really represented kind of the state of the science in terms of developing empirical modeled data sets. It's outperformed these land use regression models that have been kind of the state of the art for the past 15 or 20 years. But I do have to acknowledge that a lot of these uncertainties are not well quantified because there's not a standard way to evaluate an empirical model. And there could be a lot of large uncertainties because it's using these very unequal data streams. I'll talk a little bit more about that in the Chalk Talk tomorrow. And so what I really did not want to do was design an air pollution sensor network just based on averages. I thought that anyone could take this data set, take the average of it, and just place monitors where concentration gradients start to fall off. I wanted to design a network that can capture the most extreme transient pollution episodes that might come and go, whether that's a wildfire in a rural area or a temperature inversion in a city that stays for a week but has a huge effect on the local population. And so in order to do that, I use a linear algebra data-driven algorithm called dynamic mode decomposition. And some of you may be familiar that DMD was actually developed here at the University of Washington by Peter Schmid in the late 2000s. And so how it works at a very high level is that I have my 2D snapshots of my PM2.5 data. I organize this into a matrix X, where on one axis of that matrix is space, latitude, longitude, and the other axis is time. I have this same matrix X that is just time shifted one time step into the future. And what DMD attempts to do is create this best fit linearly approximated model A that can push these spatial temporal dynamics forward in time. It's a little bit more complicated than that, requiring some SVD and projection-based methods. But what this model A can give us is some kind of background variability or baseline variability of PM2.5, which we can use to separate from high pollution episodes. And so that's what I show in this complicated figure here, which I'll walk you through. But I wanted to have a brief aside and say that throughout my research career, that undergraduate mentoring has been this kind of large focus of mine. Over the course of 4 summers, I mentored 10 undergraduate students, which includes getting them funding and designing these kinds of independent projects. And I want to highlight several of them today here, with Samuel being a co-author on this paper. And so what I'm showing you here is a calendar, we can call it, a DMD calendar. And like any calendar, on the x-axis here is our linear understanding of time, going from 2000 to the end of 2011. On the y-axis are different pollution time scales, going from 11 years all the way down to 1 week. It's very similar to a wavelet-style analysis. And so walking you through this, we can look at the long-term variability of PM2.5 over this data set, and we see that the spatial map says that variability is higher generally in the eastern United States versus the west, except for maybe parts of California. This agrees pretty well with our long-term understanding of PM2.5 trends. So if a pollution episode were to exceed this baseline variability, I color-code it as a red rectangle in this calendar. And you notice that most rectangles are between 1 week and 1 month. This actually makes a lot of physical sense because the lifetime of PM2.5 of the surface is around a week. So I thought, let's look at some of the more anomalous events here. This is an event that happened for almost 9 months, going from 2007 into 2008. The hotspot shows the San Joaquin Valley in California. I looked in the San Joaquin Valley's air pollution control report and found that 2007 was a higher air pollution time period than the years around it. So what happened here was there was frequent temperature inversions during the winter that just capped pollution in the valley for months on end. Another one here that happened for 2 months in the summer of 2007, the hotspot emanating from Idaho and northern Nevada, and this corresponded exactly with the Murphy complex fire. It's because this underlying data set has these built-in kind of observations baked into it that we can link these kind of anomalous or really high pollution episodes to real-world events. And so what happens if I go through this calendar and I go one by one by one, the dominant signal is from wildfires in the western US. And so before I explain this plot, I want to say what's a really nice kind of feature of this calendar is it's basically a matrix. And on one axis of that matrix is space, latitude, longitude, so just a pixel in space. The other axis being these different pollution timescale events. And what we can do is find the rows of the matrix that have the largest air pollution signals across all of these time horizons. And those are the places we place sensors. It's creating this kind of greedy optimization strategy for us. And what I find is that in the eastern US, this DMD network matches the EPA pretty well, just with a reduced density. But the difference is really in the western US here. The San Joaquin Valley, or the lower Central Valley, has around 15 monitors from the EPA. DMD says there should be 5 times as many. It's one of the most polluted places in the United States, and it regularly exceeds these air quality standards. Northern California, basically wildfire country, again, an under-monitored representation by the EPA, along with areas in eastern Washington and Idaho as well. Okay, so shifting gears a little bit. The next summer, I worked with Tim here, and he is a public policy major. And what we did was, let's look at air pollution networks in cities, okay? And we wanted to look at elements of environmental justice. So let's look at urban cities with problems with air pollution, and also that with histories of income and racial segregation. And can we design an optimization framework to place monitors where air pollution variability is the highest, but also try to place it in more kind of non-white and lower income areas? And so here we look at Houston, Texas. It's this is the metropolitan area. And just considering only air pollution information alone, we place sensors kind of throughout the entire domain, right? Maybe with a heightened density in downtown Houston where there's a lot of activity. If we were to use income data from the United States Census, 2 neighborhoods pop out. One is Trinity Houston Gardens in Northeast Houston. This is a majority Black neighborhood that would otherwise be not represented here at all in this original air pollution network. And also the Ship Channel. The Ship Channel is also a very polluted place in America. It's very underdeveloped, a lot of diesel trucking, a lot of ships running through the channel. The rate of childhood leukemia is 56% higher than the national average here. So what this optimization does is being able to kind of uncover different areas that we can place sensors as well. And there are other cities I look at in this paper that you should ask me why, because they're all chosen for personal reasons. Okay, the key takeaway here is that this is the first set of studies that look at data-driven air pollution monitoring sensor networks in the United States that is both optimal, capturing the drivers of air pollution that are relevant today, but also equitable. Because we really have more considerations for sensor placement than just where air pollution is highest. There's no machine learning explicitly in this work, but I'll talk about it a little bit more in my chalk talk tomorrow. But what I want to say is that for a current state of things is that people really want to know where to place sensors. I'm working with the Harvard Public Health School, who's deploying a field campaign to monitor air pollution in Madagascar. I helped them where to design sensor networks in their areas of interest. I'm working with a PhD student currently at Stanford who's creating a PM 2.5 empirical model for India, and I helped create a sensor network that extends the current Indian government's sensor network because they want to expand that. So making policy recommendations. And also Lawrence, Massachusetts. It's a dominantly Hispanic city in the Boston metro area. They found my paper and they asked, hey, where can we place sensors for environmental justice-based monitoring using low-cost sensors? And I helped with them with that as well. Okay, so this is the last section looking at prescribed burns, and don't worry, I can see the fatigue on everyone's faces. It is shorter, Not because it's least important. If anything, this is probably the most immediately important topic. It's just that it's also kind of my newest foray into a research question. I've only been working on fires for around a year or so. So this section, we know that wildfires are increasing in size, severity, frequency in the Western US and Canada. These are due to elements of escalating climate change, but also the 100-year legacy of fire suppression policy in the United States, where the idea has been when a fire sprouts up, immediately stamp it out, which has led to these overgrowth of fuels in the West. There's this idea that maybe prescribed or controlled burning may be a way to, as a potential mitigation strategies. These are kind of practices done by indigenous communities for millennia, where you use fire to treat land and kind of clear off low-level brush. Maybe this might be a way forward because we didn't see these megafires before Europeans came on the scene. The problem is that prescribed and controlled burning in the United States is a complete socio-ecological, political nightmare. Here I'm showing you the burned area by different fire types in the United States. And you notice that in the eastern United States, especially the southeast, controlled burning is very normalized. They do it all the time. It's a very common land management strategy. Whereas in the western US, it's very much just a boutique application. Most burned area in the western US is from out-of-control wildfires, right? The problem is that you might say, okay, overcoming even the political considerations of this is horrific, but if you can ramp up the prescribed burns in the West, what does that actually mean in terms of cost-benefits analysis? We actually don't have any idea if this will even work. What you may be doing is creating this trade-off where people in the cities may not experience smoke a couple of weeks out of the year, but then these rural frontline communities are just inundated with smoke the whole year round. And so I wanted to look at these kinds of changing dynamics in the West. So I teamed up with this is a paper published last year, and I have a co-author from the United States Forest Service, and we wanted to look at recent prescribed fires in the Western US and what that looks like with its relationship to wildfires. The pixelated base map here is looking at smoke PM2.5 from these air quality models that I've talked to you about for September 2020, which is a really large high of this wildfire season in which many of you have lived through. The black dots are the satellite-derived locations of large prescribed burns, large being greater than 1,000 acres. And this is for a 5-year preceding period from this month. And you notice there's a mismatch between where these aggressive prescribed burns have taken place and where smoke was the largest. But it really varies state by state. In Arizona, in the national forests of the Tonto and Apache sickreaves, this is a very common land management tool. Central Oregon, this is largely agricultural burning on privately owned lands. But Western Oregon and Northern California, the places that you would argue might need these treatments the most, only had 7 of this size over a 5-year preceding period. And so, high chance that someone actually is from the Forest Service or Forest School here and say, hey, I definitely know that there's more than 7 prescribed burns in California. That doesn't make sense. That's right. In fact, over even a 3-year preceding period, there was almost 10,000 prescribed burns in California or Northern California. It's just that they're very small. If you look, this is a data set provided to me by the United States Forest Service from on-the-ground land managers. And they, if I filter by the size of the treatment in terms of acreage, even exceeding 500 acres or just 2 square kilometers, less than 1% of these treatments have been of this size. And so the United States Forest Service is really trying to develop a policy of maybe applying a small number of large prescribed burns instead of many small ones. Because many small ones will generate a lot of smoke for kind of these frontline communities, and it probably doesn't do anything to revert the legacy of 100 years of fire suppression in the West. Okay, don't worry, a couple more slides. And so here I want to highlight Karina Chung, who is a sophomore writing a first author paper with me, total whiz kid, where last summer we created a Google Earth Engine smoke policy risk tool of looking at the most seasonal and extreme predictions for smoke monitoring in the western US. How this works is we take data from the MODIS satellite for different land cover types in the West, assign it some probability that it will burn, how much PM is emitted when burned, and then using these outputs from these air quality models that I have run a bunch. And what we can do here is create this tool or app, if you will, of where we can find the areas with the greatest risk of the highest smoke exposure. This is in stark contrast to to a lot of models that try to predict where fires will burn. Here we try to predict where smoke will be largest, but it's still in prep. And so the key takeaway here is that states in the West may benefit from applying a small number of large prescribed burns instead of many small ones. This has been highlighted by Randy Moore, the chief of the United States Forest Service, and presented internally at the Department of Agriculture by the undersecretary. And of course, there's much more work to be done here. And in the interest of time, I'm going to skip this. This is what I'm working on currently as a postdoc, which is try to develop an intuition of applying some kind of prescribed burning or land management scenario and connecting it using both models and observations to smoke that may be produced or prevented in the future. But I want to leave you with several questions of these future ideas that I have that I want to answer in terms of a research program. It's one, is increasing prescribed burning a feasible deterrent for wildfires in the Western North America? In many ways, it makes sense on paper, but we have no idea if we ramp it up that it will even make a dent in any of these wildfire dynamics we see. Two, I believe that even though we have very unequal monitoring systems right now, that we can be doing much more with them. We can develop early warning systems for air pollution and actually resolve emissions characteristics and sources just from ambient data alone. And I believe really that machine learning integration can facilitate the next generations of these global models with these kinds of emulator type questions and problems. And again, environmental justice has been kind of this theme throughout my publication record and my research career. I didn't really get to talk about it as much today, but it's still on the horizon for my research program. And so all this is to say is I try to use these machine learning and data-driven methods to create for the pursuit of a more sustainable future. Thank you so much for your attention.
So we'll take questions or comments from the audience. And I think Makoto said he wanted to sort of manage his own questions, but I'll move the mic around if
Thank you.
anyone has any.
Hey, thanks for a great talk. I had a quick question about the wildfire piece. In terms of the southeast versus the west and the prescribed burn culture, is any of that like policy related where it's maybe more restricted in the west versus the southeast? Because I would kind of expect that.
Yeah, it's actually a huge mess. So the time it takes to approve a prescribed fire in North America right now is 4 to 7 years. So it was developed largely in the 70s, kind of through, it's called the National Environmental Policy Act. So it requires kind of community buy-in, and what it's actually been used for is kind of a lot of advocacy groups are stalling that process because they don't want these prescribed burns. So in some ways, it's a kind of an education problem that we can say that prescribed burns is actually healthy. You know, we're trying to manage the land through this kind of fire-based approach, but you know, it's like what I showed in that map. It's completely east versus west. People don't want to burn down anything in the west. You know, these national forests, national parks. It's just not part of the culture. So. There's actually a lot of other things that I can say that's more off the record to you later, but it's more of a kind of different states and different governments actually circumscribe and kind of avert these policies in different ways.
Thanks.
Thank you for the talk. My question is about the data generation piece. You mentioned dataset generation was something you found success with, and I was interested to hear more about validating the accuracy for where you're predicting data in a zone that's not being monitored. How are you thinking about that?
Yeah, so actually that movie I showed, that was not my work. That's work that was put out by the Harvard Public Health School. But you know, we see a lot of these kinds of regression-boosted tree-based methods of creating these data fusion data sets, right? The problem is that there's no real way to validate it in terms of the classic error-based statistics. You just use R squared and root mean squared errors at the locations where you have monitoring data, right? And so I propose to do this in kind of more modal decomposition-based approaches where you can kind of see the connectivity of data. Because in fact, I've worked with these data sets a bit, and just doing a simple kind of spectral decomposition is just riddled with artifacts. So you can see basically if there's a sensor with some kind of reading, there could be a huge bubble area, or you can do a decomposition and it looks incredibly pixelated, like there's so much noise. So yeah, I think we really need to kind of push for more stringent error characteristics using methods that are just not simply mean and standard deviations and things like that.
So you gave a couple of examples of impact in part 2 and part 3 of your talk.
Yeah.
I was wondering if you could speak a little bit about whether your work or other people's work where you can have impact on the first part, where using your ML for predicting of global atmospheric models.
Yeah, so the first part is more of an emulation problem, right? So the idea is to faithfully recreate or represent these implicit high-order solvers, which we've been developing for 30, 40 years, right? And so I think that actually has the longest potential range of including chemistry into climate models that we really don't have this. What does this mean? We could look at elements of chemistry-climate feedback, how it cycles with the biogeochemical cycles. We can enable greater ensembles of these climate model trajectories where we actually know kind of the uncertainties of air pollution and how it interacts with the climate system. So in many ways, that's kind of the more globally reaching potential for these applications, but I haven't done more of that yet, but that's something I'm really excited about. Thank you for the question.
I guess my question is more general, and that has to do with, so one thing we can do with machine learning and data assimilation and data fusion is bring together many sources of data and models.
Sure.
And I guess I'm just wondering, for instance, in situ PM 2.5, how much data do we really need in that environment? How can we supplement it with other data sources? For instance, satellites give us aerosol optical depth, which is a very good proxy for wildfire as well. And how do you think about that?
Yeah, I mean, in many ways, AOD is not great for surface PM because it's interpreting the whole column. But I think your point is very well taken that maybe in 10 years this might not be a problem. We're launching these geostationary satellites where we're going to have kind of this unprecedented coverage of PM 2.5 and these different NOx, ozone sources, et cetera. But we still won't have that over largely underdeveloped countries, right? So I think in some ways the developed countries, we're launching these kind of fancy satellites, but we still need to develop these kinds of methods. Can you repeat another point?
Well, it was like how much data is enough? I know that you need in situ data, including in all kinds of different environments.
Yeah.
But for instance, the history of global weather forecasting is that it used to rely on a surface network and radiosondes, and now it's almost exclusively reliant on global satellite network. And those other networks have actually decayed in many places from when they were 50 years ago.
Yeah, well, unfortunately, the best way to develop some kind of chemical intuition is retrospectively. So we don't know until we have enough data. And to answer that question, I don't know. But in terms of the satellite data, we can't just rely on AOD. So we still need these ground monitors and different kind of data fusion kinds of approaches.
So I'm wondering what the prospects are for using machine learning with a full chemical mechanism instead of a very reduced chemical mechanism, and then also how important is it to do that? Is it important?
Yeah, so I'm hopeful for the prospects. So earlier I showed you that I can go from 101 species to 16 without really loss of accuracy. Geoscam being over 200 species, it's not unheard of to maybe get it to 50 compressed features. So in terms of the dimensionality, I'm not too worried. So I guess Okay, I'm going to forget the second part, but I want to make a point that I think there are three things that are really important for this machine learning kind of solver. Is one, speed up, right? In many ways, speed up is almost automatic. Even if we have really complicated architectures, we can write it to text files, and it will just speed that up, okay? So second is accuracy. I think if you give me a GPU and more time or a more complicated architecture with more layers, we can improve the accuracy that way. The issue is stability. All of these kinds of emulator works, you emulate the process in an offline kind of setting away from the global model, put it inside, and it just is incredibly unstable and explodes. So I think what I'm trying to show you here is that even with a very simple model, a very simple mechanism, I'm still able to get stable kind of results. So I think that's the really exciting part. And sorry, I want to answer your second part that I forgot.
Is it important to
Oh, yeah.
the entire chemical mechanism or not?
Yeah, so that's another great question. I think that in some ways, that's not up to me. I think what people curate these chemical mechanisms, right? It's more of the community designs them, and they say that chlorine chemistry is important, and I could say that maybe it's not. Oh, sorry, I know you work on chlorine, but but it, kind of dampen down ozone and geoschem. We should get rid of it, but no, like the community says this is important because there are physical process linked to these. So, there's a way to maybe take the master chemical mechanism with tens of thousands of species and produce an optimal mechanism. But I want to be using something that the community kind of puts out there and says this is important for scientific reasons, not just based on an optimization problem. So I think both, yeah.
I think we have time for one final question. Maybe I'll let Makoto pick the last one.
Thank you so much for the great talk. This is also related to kind of Becky's question, but you demonstrated that online training of these machine learning chemical solvers is the most stable and accurate way to do it in your work. If you were to adapt this to like a climate model, so a chemistry climate model, which are much slower than these transport models, do you think your approach would be computationally feasible? And if not, how would you surmount that?
Yeah, so good question. I think you don't want to start with the global climate machine learning embedded model to start. I think you have to scale up your problem. What's really quite nice is that actually a paper is going to be submitted sometime later this month of CESM GC. So I showed it for geoschem, this three-dimensional kind of offline climate model with offline meteorology. But they're putting the geoschem chemical mechanism into CESM, the community climate model, right? And so I think this would be a completely natural kind of putting that machine learning solver which emulates geoschem, so we can go from offline to online geoschem, which is cheaper than CESM, and then into CESM itself. So I think there's kind of this nice natural progression. Yeah, thank you for the question.
Great. Let's thank Makoto one more time.